Okay, so November 2021 P21, we'll just have a look at it. This one will just revise the entire syllabus as we go through the questions. All right, so define density. The first part is just define density is mass per unit volume, or you can just write it in mass over volume. The one thing that I always mentioned to you guys before is that don't write it in this way. Okay, so because if you write it in this way, symbols not defined, therefore not accepted. Okay, if you go and write the density equation, this one, but the symbols are not defined, they won't accept it. So it's best to just write it in word form like this, mass per unit volume, or this one. Okay, if you want to write the equation, you can just write it as this. Now density is mass over volume. Now this one they accept. You can write it in equation form also, but with wordings, not symbols. All right. So please make sure that when they ask you to define, don't just write the equation in symbol form. Write the equation if you have to, but in words, or just use the proper word definition like this. Okay, so for B, you have a small pebble made from uniform rock that has the shape of an elongated sphere as shown in figure 1.1. The length of the pebble is L. The cross-section of the pebble in the plane perpendicular to L is circular with a maximum radius of R. When we're talking about the cross-sectional area, we're talking about this. Okay. The student investigating the density of the rock makes measurements to determine the values of L, R, and M of the pebble as follows. State the name of a measuring instrument suitable for making this measurement of L. Okay, so L we know is measuring a length. But why specifically do we use vernier caliper and digital caliper? Why is it specifically we use this? Okay, wait guys, just give me 1 minute. You guys can have a look at the question for a while. Just give me 1 minute. I need to go and get something. Okay, sorry for the interruption. Just now my baby nephew was crying, so I had to go see what happened to him. All right, okay, so let's resume back to what we were talking about. State the name of the measuring instrument suitable for making this measurement of L. Now we know L is this value here, 0.1242 plus minus 0.01 meter. Now when it comes to measurements using length, you will have learned 3 different instruments thus far. You could be using a meter rule, you could be using a vernier caliper, you could also be using a micrometer. But think about the uncertainty in each of these instruments. Your meter rule has an uncertainty of 0.1 meter. Vernier caliper by right is 0.01 centimeter. If you change it to meter, you're going to get 0.001 meter. You divide by 10 to get this value. And then micrometer was 0.01 millimeter. You change it to meter, it will be 0.01 times 10 power minus 3 meter. It's going to give you 0.00001 meter. Okay, so this one has, you see, 2 zeros. This one has 3 zeros. You look at your instrument here, they tell you that your uncertainty of your measurement was 0.0001 meter. Okay, so in my case, wait, sorry, 0.001 meter. So in my case, it should have been this one. Oh, sorry. Did I do this one wrongly? Digital caliper, my uncertainty is plus minus 0.1 centimeter. 0.1 centimeter. Wait. Times 10 power minus 2. Oh, sorry, this one I did it wrongly. 0.01 centimeter is times 10 power minus 2, right? So this one will be 0.0001 meter. Okay. So yeah, my mistake. I did the multiplication wrongly. So if you look at this one, L is having an uncertainty of 0.0001. This one is having 3 zeros. This one is having 3 zeros. This one I calculated wrongly. This one is 4 zeros. Okay, so based on this one, you look at the uncertainty. Which one you would have to use? You have to decide based on the uncertainty given. All right, 0.1 meter is too big. Okay, and then micrometer is too much. So the only one that seems to match is your vernier caliper. Okay, because just by looking at the uncertainty itself, you would be able to see that it is actually vernier caliper. Okay, that's why your answer here is caliper, not any of the other ones. Okay, and then for part 2, determine the percentage uncertainty in your measurement of R. So this one by right, I think you guys should be quite familiar with it already. Percentage uncertainty is just delta R over R times 100%. Just take whatever values you have for R and your absolute uncertainty, divide them with each other. The absolute uncertainty divided by your measured value times 100%, you're going to get 0.592, sorry, 0.952%. Okay, so that one is okay. Then we move on to the next one. Okay, then after that, they tell you the density of the rock from which the pebble in B is composed is given by this equation where density is mr power n divided by kl, where n is an integer and k is a constant with no units. That is equals to 2.094. Okay, then use SI based units to show that n is equal to -2. Right, so for this one, there are some ways you can, there are different ways in which you can do it. Usually for this kind of thing, when they ask you to find the units of something, in my case, they want to find r power n, what's n itself. I usually make the variable the subject. So if let's say I have rho is mr power n divided by kl, I make r power n the subject, I get rho kl divided by m. So from here, the unit of r raised to the power of n is the unit of rho kl over the unit of m. So unit of r is length, is meter power n. Unit of density is kg per meter cube. Unit of length l is m. Unit of k is no units. They already told you here that k has no units. Okay, so you just leave that out. And then the unit of capital M is basically kg. So you simplify this, eventually you get m power n equals to m power minus 2. So eventually you'll be able to see that n is -2. All right. Now it's also perfectly fine to just leave things as it is, where you just say that rho is equals to mr power n divided by kl. You just straight away just put the units in, you'll be getting the same answer. In your case, you'll be getting kg meter per cube, kg meter power -1 for density, mass is kg, unit of r power n is meter power n, unit of L is meter, unit of K don't need to consider. You simplify this, eventually you get m power minus 3 and then m power n minus 1. So if you just compare the powers, you're going to get this. You will get back the same answer. So no issues there. All right. Okay, then after that, we go to the part where you're supposed to calculate the percentage uncertainty in rho. Okay. So in my case, rho is mr power -2 divided by kl. This one would be the resulting expression. So a little recap of what you learned in uncertainties chapter last time. In general, if you have y equals to a plus b or y equals to a minus b, you're going to get delta y is delta a plus delta b only. If you have y equals to a times b, sorry. If you have y equals to a times b, or y equals to a divided by b, then you're going to get fractional uncertainty of y equals to fractional uncertainty of a plus fractional uncertainty of b. Now the other form will be y equals to a power m, b power n, or y equals to a power m divided by b power n. This one, you would have to bring down the powers. Okay, so in my case, this one will be fractional uncertainty of y is m times of fractional uncertainty of a plus n times the fractional uncertainty of b. Okay, wait on. This one, just be careful. Ignore any negative in the powers. Okay, what you're doing was that you're bringing down the powers, right? In some form or some variations, sometimes you will get a negative sign there. So just ignore any negative in the powers, right? For example, if I tell you y is equals to a power 3, b power negative 2, if I give you something like this, a is power 3 divided by b power 2, this one can be written as, if you just look at this one clearly you will write it as delta y over y equals to 3 times delta a over a plus 2 times delta b over b, right? Now this same equation, if you look at it, you could have also written as a power 3 b power minus 2. So does that mean that this one will become like this? Yeah. Does that mean that just because of that, you're going to have minus sign delta b over b, 2 times delta b over b? Right? You see, suddenly, how come this one suddenly becomes different? By right, this was the same as this, but suddenly now I'm getting two different equations as a result of me considering the negative sign inside. So that's why I mentioned to you, just ignore any negative sign. All right? Don't bother putting negative sign in. Right? Just ignore any negative sign. And also another thing to note here is that the other reason why we don't put negative is because uncertainties will only add up with more measurements. Okay, they do not subtract. They do not subtract or reduce. Okay, let's just say you want to get the value of quantity y. You take measurement A, you take measurement B, you take measurement C, D, E, and F, and then after they use them together to calculate the value of y. Because your measurements each have uncertainty, if you do more and more, your uncertainties will only add up. They're not supposed to reduce. They're not supposed to subtract from each other. Okay, so that's another reason why we don't put a negative. Because if you do more measurements, it doesn't make sense for their uncertainties to reduce. It will only add up. Okay, so back to what I was talking about for this question. This negative 2, just ignore the negative. All right, it's supposed to be positive. So this one will be plus 2 delta R over R plus delta L over L. This equation is similar to this form of equation. All right, we're following this form. Okay, so from there, you just sub in your values. 0.01 divided by 1.072 plus 2 times 0.004 divided by 0.0420 plus 0.0001 divided by 0.1242. You're going to get this. Okay, this one is actually just fractional uncertainty. You need to multiply by 100% to give you percentage uncertainty. Okay, so while we're in that part, let me just rehash a little about something else. if you have something y plus minus delta y is known as your absolute uncertainty. Okay, this is number one. Number two, delta y over y. Maybe I shouldn't use a bracket here. This one is known as your absolute uncertainty. Okay, sorry. Delta y over y is known as your fractional uncertainty. And then after that, the last one you would learn is percentage uncertainty. This one is known as your percentage uncertainty. Okay, so these are the three different types of uncertainty that you would be using. Just be careful about what the question wants. Do they want absolute or fractional or percentage uncertainty? In your case, you're asked for percentage uncertainty. So please make sure you code your values in percentage uncertainty. What you have here just now, as I mentioned, is just fractional uncertainty. To change it to percentage uncertainty, you will just need to multiply by 100. Okay, so wait, from this one, basically it's like this now. From fractional to percentage uncertainty, you times 100%. From percentage uncertainty to fractional, you divide by 100. Okay, that is the thing that usually you would need to know lah. Okay, divide by 100. Okay, and also one last thing in terms of your SF. For absolute uncertainty is usually one SF only. Okay, your questions won't ask you to. The questions expect you to know this. All right, they expect you to code your absolute uncertainty in one SF only. Okay, but for fractional and percentage uncertainty, this one can be 2, 3 SF. All right, it's only your absolute uncertainty that you need to be careful about because they always want one SF only. This one has to be remembered. But for the others, fractional uncertainty or percentage uncertainty, you can treat them like normal. Just write them 2 or 3 SF. Okay. So eventually your answer is this one. Okay. The last part here, they ask you determine rho with its absolute uncertainty. Give your values to the appropriate number of significant figures. Okay, give your values to appropriate number of significant figures. Okay, so the absolute uncertainty, basically they just want the delta rho. All right, if you know, for example, that delta rho over rho is 0.0208, which is what you did over here. If only you know what is rho, you can find out what is this. This one is your absolute uncertainty. Okay, so they're asking you for the delta rho here, right? But before you can find delta rho, the absolute uncertainty, you need to find out what is rho, the density first. Okay, so that's why here your workings, you have to find out the density first. Use back the original equation, mr power -2 divided by KL, sum in all your relevant values, eventually you get this. Okay, once you have this, you can then find this. All right, so in my case, if let's say I do the workings over here, delta rho over rho is 0.0208. I already found out what is rho is 2.34 times 10 power 3, and then this one was the fraction. Find out what is delta rho. I'm going to get 0.049 plus times 10 power 3, and then what I do is that I express your absolute uncertainty to one SF only. In my case, this one will be 0.05. Okay. All right. When you try to express your absolute uncertainty, what is the power of 10 that you want to express it in? There's a hint from that. Wait, let me just clear out the drawing. When you first calculate out your rho, you notice that this is 10 power 3, right? So when you eventually find out your absolute uncertainty, you try to match your power of 10, match the power of 10. Let me just write it properly. What you try to do usually is that you match the power of 10 POT for calculated value and absolute uncertainty. Okay, try to match it. Okay, because there was one rule that you would have learned last time when expressing uncertainties with their when expressing a calculated value with their uncertainties. That one was this one. If let's just say I told you y is equals to 4.13 plus minus 0.05, the first rule was that this one is 1 SF only. Okay, this one is 1 SF only. This is rule number 1. And then rule number 2 is that you need to follow the DP. So in my case, you can see that this one was 1 SF, 2 DP. So this one, when you express it, it must be 2 DP. Okay, that was the rule. Always look at the SF of your absolute uncertainty first, only then you match your calculated value DP. Okay, now, but there are some cases where you cannot see your decimal place easily. Like in my case here, if I just look at this one here, right? If I match the power of 10 for calculated value and my absolute uncertainty, you'll notice that you can actually see the decimal places easily for this one. So you see, in my case, this one here was 2SF. Let me just write this out. This one here, you notice it was 2SF, but 3DP. So the problem is that this one is not 1SF. So you have to re-express it in 1SF. So in the process of you expressing it in 1SF, this one becomes 2DP. All right. So when you go and express your calculated value with its absolute uncertainty, the calculated value now must have 2DP following this rule that I just wrote here. That's why your answer will be 2.34 plus minus 0.05 times 10 power 3. And that is one way of doing this. Okay, but then there's also another different way also. This one is if your values are not having any decimal places to work with. You see, for my case, because I express this in terms of 10 power, in terms of power of 10, there's a power of 10 here, my values tend to have a decimal place. In some cases, there are values that you don't express with decimal places, or you're just not given in terms of decimal places. What do I mean by that is that you look at the statements in the, you just look at the writings that are already written here. If let's just say I recalculate everything for you, okay. Density I know is 2337. This one I don't write it in terms of power of 10. I just write it as it is. Okay, density is 2337. I don't write it like the form I have here. This one I don't write it with power of 10. This one I don't write it with any decimal places. Then after that, I proceed to find out the absolute uncertainty. Delta rho over 2337 times 0.0208. I'm going to get delta rho as 49. But the problem here with this is that this one is 2SF. I want to change it to 1SF. So this one changed to 1SF becomes 50. But in the process of changing it to 50, you notice you don't have any decimal place to consider, right? 49 to 50, there's no decimal place to consider. So if you don't have decimal places to consider, you consider whether are you rounding it out to the nearest 1, nearest 10, nearest 100, or nearest 1,000. So in my case, you see, me rounding it out from 49 to 50 is actually rounding to the nearest 10, okay? So when I want to express my values, it could have been, I mean, if I express my values, the values as it is could have been something like this. Yeah, maybe I write the top, it's easier. If I write the values as it is right now, rho is 2337 plus minus 49. Okay, if I just write the values as this is right now. But you see, the problem is that this one is 2SF. So I need to change this to 1SF. When I change this to 1SF, 49 becomes 50. But in the process of me changing from 2SF to 1SF, this one was rounded to nearest 10. So since it's rounded to nearest 10, my calculated value must also be rounded to the nearest 10. Okay, so in my case, you see, 2337, if I want to round it to the nearest 10, it becomes 2340. Okay, so this is actually my original value. This is supposed to be, this will be the correct value. 2340 plus minus 50. So in cases where you don't have decimal places to work with, just look at whether you're rounding to the nearest 1, 10, 100, 1,000, or whatever when you're trying to round out your absolute uncertainty. Your answers will be the same as if you had used with decimal places. The example would be what you have originally. If you look at the original working here, this one was using with decimal places, right? You get 2.34 plus minus 0.05 times 10 power 3. If you were to put your 10 power 3 inside, you notice you're going to get 2,340 plus minus 50, right? Isn't this answer the same as what you have here? This one is also 2340 plus 50. Okay, you are basically getting the same answer, all right? So when it comes to the exam, it's up to you which one you want to use. Either you want to use with decimal places, or either you want to just use it as it is, just round to the nearest 1, 10, or 100. Personally, I find this easier lah, if you don't have a lot of if you don't have decimal places to work with. Okay, but it's up to you. All right, just familiarize yourself with either one. Okay, so that one is okay. Then I move on to question 2. All right. Okay, now define momentum. Momentum is either just product of mass and velocity, or you can just write it in word mass times velocity, because you know that P is mass times velocity, right? Okay, so just put it in words and you'll be getting the answer. Okay, now then the other two, for the other question, two balls X and Y of equal diameter but different masses, 0.24 kg and 0.12 kg respectively, slice towards each other on a frictionless horizontal surface as shown. Both balls have initial speed of 2.3 meters per second before they collide with each other. Okay, they all have different masses. Figure 2.2 shows the variation with time of force Fy exerted on ball Y by ball X during the collision. Fy is basically the force on Y, all right? Then after that, this is what you're gonna get. They ask you right now to calculate the kinetic energy of the ball X before collision. Okay, diagram is talking about Y, but question is talking about X. So please be very careful when you read your question. So what is the kinetic energy of ball X? You know the mass, you know the speed. So this one is pretty straightforward. Your KE is going to be half mv squared is half times 0.24 times 2.3 square. You're going to get the answer as 0.635 joules, just like this. Okay, so this one, no issues. Just by doing this, you're already going to get 3 marks. Okay, then we go to the next part of the question. They tell you the area enclosed by the lines and the time axis drew in figure 2.2 represents the change in momentum of ball Y during the collision. Find out the magnitude of the change in momentum in ball Y. Okay, this one was something that you would have learned under the dynamics chapter where we told you that force is actually rate of change of momentum. Okay, so this one, you rearrange this, you're gonna get this. This one, change in momentum is equals to force times time. This is actually the area under your force time graph. Okay, this one was the understanding that you would have learned in your AS by now. But your question made this simple for you. They didn't really expect you to recall this. They straight away just tell you the graph, the area under it is actually the change in momentum, which actually correlates to what you learned here. Okay, find out the change in momentum of ball Y. So all you just need to do is to divide this little thing into 2 separate areas, area 1, area 2. There are 2 triangles here, 1 and 2. So just find out the answer from there and you should be okay. So this is 0 to 3, 3 to 5, this is 3, this is 2, this one is 200 divided by 10, so each one is 20. This one is actually going to be 240. Okay, so hence just sub everything in, find out the areas of the 2 triangles. Remember to change your time from milliseconds to seconds. That's why there's a 10 power minus 3 here. Eventually, you're going to get the answer as 0.60 Newton seconds. Okay. So let me just clear off the things that you're seeing right over here. Okay, so you're going to get the answer as 0.60 Newton seconds. Okay, yeah, another thing I should mention here is this. When you do your calculations in your calculator, you may be given this answer 0.6 and then you may have unconsciously just written it as this. This one, if you write it, is 1 SF. You will incur a penalty. I told you before, final answer, minimum 2 SF, maximum 3 SF. So sometimes people forget when they're doing using your calculator, they straight away just write whatever they see. They write it as 0.6. The moment you write something like this, they will minus 1 mark. Okay, so write it as minimum 2 SF. That's why the answer is 0.60. Okay. All right. Okay, so that one is okay. All right, then after that, part 3. Okay, part 3, if you're not careful, you might get some wrong answer. Okay, this one is something that I think I should probably mention to you guys first. All right, let me just give you a very simple example. Before that, let's just read the question. For part 3, calculate the magnitude of velocity of ball Y after the collision. Here, they want you to calculate the magnitude of the velocity of ball Y after the collision. They want the magnitude of ball Y after collision. But then you have a problem here, you see. I mean, if let's say you want to calculate the velocity of Y after collision, you might have tried to use conservation of momentum to find the velocity of ball Y. That is one of the standard methods of doing this. But in your current question, you cannot do this right now. Why? Because You see, the only information that is given to you in this question was the initial case. The initial case before collision, right? The only information you have is before collision. After collision, velocity and direction of x is unknown. Velocity and direction of y is also unknown. Okay, so you actually have 4 unknowns. Okay, you actually have 4 unknowns here, because based on what the question has mentioned to you, you don't know any of these things. For x, you don't know the velocity nor direction. For y, you also have the same case. You actually have 4 unknowns. So you want to use conservation of momentum when you use the m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. You can only use this if only there is one unknown. Okay, so you might have been tempted to try and use conservation of momentum to do this, but then eventually you find out you're stuck because there are too many unknowns here. You just do not know 3 more things. Okay, that's why here, when they ask you to find out the magnitude of velocity of ball y, you can't really use conservation of momentum. So the hint would come from what you have done before in the previous question. Remember, in the previous question, you actually found out the change in momentum of ball y. The previous question here, you actually tried to find out the change in momentum of ball y. So in the absence of any other method, most of the time, the hint will be from your previous question. Okay, they ask you to find the change in momentum in ball y. So this one, you could try to make use of that to find out the magnitude of velocity of ball y. So what are the things that you can do? Now, in my case, actually, I can actually deduce out the direction of ball y. Okay, the direction of ball y can actually be deduced. You see, this one is 2.3 meter per second. This one is 2.3 meter per second. But this one is 0.24. This one is 0.12. This one is larger mass, right? Mx is more than My. Ux is the same as Uy. I can actually say that the momentum of X is more than momentum of Y. Basically, this one has a larger momentum in this direction when compared to this direction. Okay, wait, let me just write things properly. In my case, for X, you ought to have a momentum in this direction. For Y, you have to have a momentum in this direction. Okay. But looking at how things are, these two initial velocities are the same for X and Y, but mass M is more than mass Y. Its mass is larger. Obviously, the momentum of X will be larger than Y. So from here, you can actually deduce one thing. After collision, Y moves to the right. Okay, just by looking at this diagram, you can guess that Y is actually going to be moving towards the right because it's being Y is being hit by something with larger momentum. Obviously, it's going to be deflected off. Okay. Okay. So with that in mind, you can say something like this right now. Okay, just bear with me for a while. You cannot say that, oh, before collision, your object Y was moving like this. This is before. But after collision, it's moving like this. Okay. So this is the before and after case. Before you had 0.12 kg going with a velocity of 2.3 meter per second. After you also still have 0.12 kg, and this is the velocity y that you want to find. Okay, so you make use of the question from before, where you already found out the change in momentum as a result of the collision. Okay, now here is that one thing here that where you need to be careful about. Now, change in momentum, it can be final momentum minus initial momentum, or initial momentum minus final momentum. Either one doesn't matter. You can take either one. Final minus initial, initial minus final. Okay, so doesn't matter which one. It doesn't matter which, but make sure direction is considered properly. Okay, so let's just say, for example, right now I want to just for the sake of just for the sake of discussion, let's just say I want to just take final momentum minus initial momentum. Wait, let me just see which one should I take. Okay, I'll just take the, for my case here, final momentum minus initial momentum. Okay, I will take the final momentum minus initial momentum. You will see something a bit odd here later on. Okay, so I'll just write it here. Now, if you take final momentum, the change in momentum as final momentum minus initial momentum, set your sign convention. This is one of the things I mentioned to you guys last time, to set your sign convention. So if let's just say I mentioned that going towards the right is positive, and then right now I'm taking final momentum minus initial momentum, the final momentum would just be 0.12 times V. Yeah, Vy. Maybe I just, okay, maybe I don't write Vy, I just write V. This one will be 0.12 times V minus with negative minus with, how do I put in the negative here? Okay, I'll put it inside the speed. This one would be 0.12 times with negative 2.3. Okay, this one, let me find a better place to write it. Wait on, let me just this. I'll write it at the bottom here. Change in momentum is final momentum minus initial momentum. If I assume that going towards the right is positive, this is what I'm supposed to be getting. I'm going to be getting 0.12 times V minus off with negative 0.12 times negative 2.3. Okay, because this one is negative, this one is negative, you eventually get the conclusion that they're positive. Okay, so you eventually get to the conclusion that they're actually going to end up being positive here. Okay, so you found out your change in momentum at 0.6. Okay, now when you do this, your answer should be correct, where you're gonna get the answer as V equals to 2.7 meter per second, which is actually what I wrote here, actually. Okay, This one, if you do it like this, you're going to get the answer as 2.7 meter per second. That's correct. Okay, but what if you set your sign convention a bit differently? In my case, if I said that delta rho, okay, I'll write this at the top. If I say that my sign convention is going towards the left as positive, my initial, my change in momentum would still be PF minus, this time is negative PF minus with PI. Okay, so this one here, as I mentioned, is my PI. This one here is my PF, right? So my sign convention is going towards the left as positive. This one PF would be negative. That's why there's a negative sign here. Then my PI is in the same direction as my sign convention, so there's no negative sign here. So now if I try to sum in the values, you will notice that you might get a wrong answer eventually, a different answer than usual, just because you change the sign convention. So my PF was 0.12 times V minus 0.12 times 2.3. Now, from here, if you write 0.60, your V, you will get a very different answer. 0.6 plus 0.12 times 2.3 divided by 0.12, you're getting the answer is 7.3 meter per second. So how come is different than the correct answer of 2.7? I mean, you have seemingly done the question correctly, right? You set the sign convention. You make sure that your momentum is matched to your sign convention. In my case, PF is opposite to my sign convention. Obviously, it's going to be negative. And then PI is also, PI right now is in the direction of my sign convention. So it's obviously positive. But then when I go and sub in everything, I don't seem to be able to get the answer. There's nothing wrong with the calculation here, but somehow I'm still not getting the answer. It's because there's something that you may have missed out. Okay. Your momentum change also has direction. When we do this, usually most people will be bothered about PF and PI, the final momentum, initial momentum, their direction. But they somehow, in some cases, they also neglected the direction of momentum change. Okay. Here, momentum change direction is always in the direction of force acting on the object, or force acting on object. Okay, wait. So it's in the direction of force acting on object. Okay, momentum change direction is always in the direction of force acting on object. Okay, this one I actually mentioned it before in the notes. Let me just show you what I meant by that. If you remember the AS notes under the dynamics chapter, the first page itself, there's one statement that I mentioned. Direction of momentum change is in the direction of force exerted due to the momentum change. That time I give you the example of, say, a ball that is being released downwards. It falls down to the ground and then it rebounds upwards. In my case, we know that if the ball falls down and then it rebounds upwards, the direction of our force will be upwards, because this is the one that causes the ball to rebound upwards, right? So because the force acting on the ball is upwards, this is also the direction of our momentum change. That's why I drew it here like this. My momentum change is upwards, my force is also upwards. Okay, so with that in mind, if you look at our current question, this object Y was moving towards the left, it hit ball X and then it rebounded in this direction. Okay, so for it to go from towards the left and then going back towards the right, this would have implied to you you have a force acting towards the right. Okay, this is the direction of your force. And this will also be the direction of your momentum change. Okay, so in my case, I know this force on Y is to the right. Therefore, change in momentum is also to the right. Okay, so now with this in mind, you now look at your original working for this one on the left side. Now you see my case here is that momentum change is to the right, but here my sign convention was to the left. You see, my sign convention was to the left is considered positive. So if my momentum change was to the right, by right, this one should have been negative. But here, I actually did not put the negative. That's why you see my answer became 7.3 meter per second. It was not the correct answer. Now you see, if you go and change the answer, the momentum change to negative, you will get the correct answer. Let me just write it down here. If you write it properly, negative 0.6 equals to 0.12b minus off with 0.12 times 2.3, you're going to get b as 7.3 meter per, sorry, you're going to get b as 2.7 meter per second. Okay, right, so you're going to get the correct answer now just by putting in the negative. All right, so that's why this one you need to be a bit careful sometimes if it comes to the momentum change. Negative 0.16 plus 0.12 times 2.3 divided by 0.12. Yeah. Oh yeah, sorry. You're gonna get the answer is negative 2.7. All right, but the question actually just wants magnitude, so the negative actually doesn't really matter. If anything, the negative here just tells you that your velocity is opposite to your sign convention. Okay, so it tells you quite a number of things. Wait, let me just write this out. You're going to get negative 2.7 meter per second. Okay, this is the correct answer, right? But your question just wants magnitude, so if you just write 2.7 is fine. This negative here just means that V is opposite to your sign convention. V is opposite direction to sign convention. So in this case, it should be V to the right. V is to the right. V is to the right. Our sign convention is leftwards positive. If I'm getting a negative sign here, it means it's opposite to that sign convention. I'm supposed to be, the V is supposed to be to the right. Okay, right? So just be careful about this question. It's seemingly easy, but then if you set your sign convention wrongly, you might get the wrong answer. Okay. Okay, there's one last part to this question here. They told you on figure 2.3, sketch the variation with time t of force Fx exerted on ball X by ball Y during the collision in P. This time they're asking you to find out the force on X. The previous graph was force on Y. So the only thing you really need to remember here was this. This is related to Newton's third law, where we mentioned to you that when objects when two bodies interact, when two bodies interact, when two bodies interact, they exert equal but opposite forces on each other. Okay, so the two bodies now is X and Y. They would have to exert equal but opposite forces on each other. So right now, if you look back at the graph, Fy was this line here. Fx by right should be equal and opposite. So if just now here you had 240, you should be having negative 240 at the same time. So negative 240, this one being 0, this one being 0. Your resulting line would be this one here. Sorry. Your resulting line would be this one over here, and then this one over here. Okay, this is supposed to be your Fx graph. Okay, just to show that they are equal opposite to each other. So you just translate that same graph over the other end, you should be getting something like this, no? Okay, you should be getting this graph here. Okay, so just make sure you translate it to the correct values. Okay, so this one, okay. Then we move on to part 3. Part 3 will be very straightforward. Okay, now 3A. A uniform metal bar initially unstretched has sides of length W, X, Y as shown in figure 3.1. The bar is now stretched by a tensile force F applied to the shaded ends. The changes in lengths X and Y are negligible. The bar now has sides of length X, Y, and Z as shown in figure 3.2. Determine expressions in terms of sum or all of the variables F, W, X, Y, and Z for the stress sigma applied to the bar, the strain epsilon, as well as the Young's modulus. So this one is really just a matter of your definition questions. So what we do know is that when it came to your definition questions for deformation of solids, we know that stress is force over area. Strain is extension over original length. Young's modulus is stress over strain. So in our case, we need to apply it to this question. For stress, our force is this F here, but our area is the area perpendicular to the force, right? So our area here would be this one here. Okay, this one is our area. So our area is actually the product of X times Y. Okay, so this one is all right. Then after that, yeah, they told you that the changes in lengths of X and Y are negligible before and after loading. That means no change in A. It remains constant. Your area remains constant. That's what you're supposed to just understand from that statement. Okay, for your strain, epsilon, your extension, if you recall the original length of your beam, it was actually W. Now is Z. So your change in length is going to be Z minus W over your original length, W. Okay, this one is your original length, L. Okay. So it's Z minus W over W instead. So Z minus W over W. And then after that, lastly, your Young's modulus is stress over strain. Just take the two ratios of these two values. So it's F over XY, Z minus W over W. You're gonna get FW over XY, Z minus W, which will give you this answer. Okay, so these are your answer. F over XY, Z minus W over W, and then after that, FW over XY times Z minus W. This one is pretty straightforward. Okay, right, so for this. Okay, then the next thing we'll go through is part B. A copper wire is stretched by a tensile force that gradually increases from 0 to 280 Newton. The variation with extension of the tensile force is as shown. State the maximum extension of the wire for which it obeys Hooke's law. Okay. So here the keyword was asking you to find the maximum extension of the wire for which it obeys Hooke's law. Okay. Now, what is Hooke's law? Hooke's law was this, right? Hooke's law tells you that force is directly proportional to extension. Okay, now wait on, let me just say that force is directly proportional to extension. Hooke's law was basically just saying that force is directly proportional to extension. Okay, so in an fx graph, it is represented by a straight line. In the fx graph, it is represented by a straight line that passes through the origin. That passes through the origin. Okay. All right. So that is what we know from Hooke's law. Force is directly proportional to extension. In an fx graph, it is represented by a straight line that passes through the origin. So of interest to us is the point where Hooke's law is still obeyed. The question wants the maximum extension of the wire for which Hooke's law is obeyed. So what we want to find is the limit of proportionality. Okay. It's at the limit of proportionality that your force is still directly proportional to extension. It's at your limit of proportionality that you know that your force is still directly proportional to extension. Okay. So what you want to do here is, how do you find this limit of proportionality? You try to use your ruler and then try to match it with the initial part of your graph. If you try to use a ruler and try to match it with the initial part of your graph, the straight line portion of your graph, you start to see that your graph will start to deviate. You see at this point here, it actually starts to deviate. That's why I know that this is my limit of proportionality. Force is still directly proportional to extension up to this point. Okay, so Hooke's law is obeyed up to this point only. After that, Hooke's law is no longer obeyed. So my maximum extension will be up to here only. Okay, so at the limit of proportionality, extend your line downwards, see what is the extension. You will get the answer is roughly around 22.2 millimeter, but your choice of answer can vary. The marking scheme gives you a range. As long as your answer is between 2 to 2.4 millimeter, you will be getting the marks. Okay. So find the limit of proportionality, which is the point to which Hooke's law is still obeyed. The extension there is the maximum extension. All right. So far so good. Okay, so that one is okay. Now for figure 3.3, determine the strain energy in the wire when the tensile force is 120 newtons. Okay, so let me just clear off the drawing. Strain energy is actually always the area under your graph, specifically area under your force extension graph. So in my case, I want to find out the strain energy for a tensile force of 120 Newton. 120 Newton is over here. So I want to find out the area under the graph, which is indicated by this little region here. This one is the area of a triangle. So I'm trying to find the area of a triangle here. So it's half F times the X. My extension here is 1.4 times 10 power minus 3. Okay, so that's how you do this. Yeah, there's something else you could probably add from the graph previously. You could probably just draw this one if you wanted to in your graph. Just like I mentioned to you that your limit of proportionality is up to here, right? You can probably just try to indicate on your graph something like this. This one, Hooke's law, obeyed. This one to here. Maybe I use a different color. This one up to here. Hooke's law not obeyed. Now for part 3, explain why the work done in stretching the wire to an extension of 12 mm is not equal to the energy recovered when the tensile force is removed. Okay, why is it that the work that you have done in stretching the wire to 12 mm is not equal to the energy recovered when the tensile force is removed? Okay, there are a few ways, there are some ways to look at this. Let me just illustrate to you. If I just refer back to this little diagram here that you have, if elastic limit is not exceeded, okay, if elastic limit is not exceeded, I could get a case that looks like this. This one, I load it, it goes all the way up to here. Okay, let's just say that my elastic limit is here. Okay, but I didn't load it all the way to the elastic limit. I just load it all the way to here. Okay. Just load it all the way to here only. This is force versus extension. So this one is the loading case. This one is the work done. So if let's just say I unload the material right now, I still have that same force extension graph. If I unload the material, it will go back through the same line. Okay. So this one, as I mentioned, this is still my elastic limit. So in my case here, when I unload the material, this one is the work recovered. Okay, let me just write it properly, the wordings. This is the work recovered. Alright, so in my case, work done is the same as the work recovered. So this one was the unloading case. Okay, one of the characteristics of elastic limit not being exceeded is that there is no permanent extension after unloading, i.e. no plastic deformation. Okay, this is what we should know. If you did not exceed your elastic limit, there's no plastic deformation. There will be no permanent extension after unloading. But what if you have exceeded the elastic limit? So if you exceeded that less than limit, this is what is going to happen. Okay, well, maybe I just make use of the same diagram. Yeah, I think it's better if I make use of the same diagram. If elastic limit is exceeded, so if elastic limit is exceeded, this is what you are supposed to get. It's the same diagram. Maybe I just write it down here. If elastic limit is exceeded, let's just say your elastic limit was here just now. You go and load it all the way past your elastic limit. What color can you use? Let's just say you load it all the way past your elastic limit. You load it all the way here. So when you unload it, oh wait, this one I cannot use. Yeah, sorry, this one I cannot use by the same diagram. My mistake. Let me just draw it out very quickly for you. If elastic limit is exceeded, okay, let me just write it here. If elastic limit is exceeded, your graph will be something like this. If let's just say this is my EL, I go and load it all the way to here. This is the loading case. Okay, F versus X. It's the same thing. This one here will be the work done. The area under this graph will be the work done. But then after that, if I unload it, if I release the force, what you're going to see is something like this. This is force versus extension. If I release it, this one here being my elastic limit, this one here being the force, the point that I loaded my material. Once I unload it, it won't follow back this same line. Okay, it won't follow back the same original line that the loading part took. The loading part took. Instead, it's just gonna follow a line that looks like this. It's gonna follow this line like this. This is the unloading part. Okay, it will follow a path that looks like this if I already exceeded my elastic limit. The previous one was that you load it, it follows this curve, but because you did not go past the elastic limit, during unloading, it follows back the same curve. The error under the graph is exactly the same. So whatever work that's done is the same as the work that is recovered. But after your elastic limit has been exceeded, you would have two different areas now. For this case here, during the loading case, this is the area. This is my work done to stretch the material. But once I release my load, once it falls back, it won't follow back the same curve. Okay, it will follow this blue line here and then go back to this point. You see, once it goes back to this point, this one here is permanent extension. All right, and this little area here is the work that is recovered. Okay, so your work done and work recovered is not the same. Okay, it's less. So what actually happened here is this. Wait, no, let me just redraw this. One color can I use? No color, yellow. Okay, this little area here is the work done to permanently stretch the wire. Okay, this area here, the yellow area here. Okay, The yellow area is the work done to permanently stretch the wire. The orange area is the work that you managed to recover from unloading. Okay, so the question is asking you right now, why is it that the work done in stretching the wire is not the same as the work recovered? Okay, now in my case here, because you have stretched the wire quite a fair bit here, it's sensible to assume that you have already gone past the elastic limit. Okay, so your answer will be something like this now, where you say that the wire has gone past the elastic limit, thus the deformation of the wire is now plastic. Okay, energy that cannot be recovered was used to permanently deform the wire. Okay, basically you can just say that some of the energy that was used to stretch the wire has now been used to permanently deform the wire instead. Okay, so 2 marks. You say wire has gone past elastic limit, thus the deformation of the wire is now plastic. The energy is now used to permanently deform the wire. You can, this one here, the word, the phrase was energy that cannot be recovered is used to permanently deform the wire. If you want to make more sense of it, you can actually say that part of the initial energy is used to permanently deform the wire. You can also write this now if you want to. Part of the work done initially has been used part of the work done initially has been used to permanently deform the wire. Also can, all right. You can also replace it with this statement. Either you say energy that cannot be recovered is actually used to permanently deform the wire, or you can just say that part of the work done initially has been used to permanently deform the wire. Okay. Okay, so this one is okay. Then after that, I will move on to the other one, the other part of your question. This one is question 4. All right, now by reference to direction of transfer of energy, state what is meant by longitudinal wave. Longitudinal wave is where oscillation of particles are parallel to the direction of energy transfer. Okay. Now, if you say oscillations of particles are parallel to the direction of wave travel, this one is not correct because the question says by reference to direction of energy transfer. So if you just follow what was written in the notes where you say oscillation of particles is parallel to direction of wave travel, you would be marked as wrong because they want you to refer to direction of energy transfer. So you instead say parallel to energy transfer. Okay. Energy transfer and wave travel is same direction. Okay. So if you see a wave traveling to one particular direction, energy transfer is also to that particular direction. Okay. Okay, so then we move on to part B. Part B is on Doppler effect. So let me just go through this question. Okay, now you have a vehicle that travels at constant speed. You have a vehicle that travels at constant speed around a wide circular track. It continuously sounds its horn, which emits a single note of frequency 1.2 kilohertz. An observer is a large distance away from the track as shown in the view from above in figure 4.1. So your observer is right all the way here, and then you have your vehicle traveling in a wide circular track following this path over here. Okay, so figure 4.2 shows the variation with time or the frequency f of the sound of the horn that is detected by the observer. This one is actually talking about your f0, your observed frequency. The time taken for the vehicle to travel once around the track is t. So to go from one complete round like this, it takes t. Okay, so that is what we know right now. So the variation of frequency, observed frequency with time is given by this graph here. You see your observed frequency goes up and down, right? Like this. So this one is your max frequency, this one is your minimum frequency. So from here, what they want you to explain is this. Explain why the frequency of sound detected by the observer is sometimes above and below 1.2 kilohertz. Now, what was 1.2 kilohertz in the first place? The 1.2 kilohertz over here is actually from the vehicle itself. All right. This is the original frequency of the vehicle. This is actually your FS, your source frequency. Okay, the car is emitting sound of frequency 1.2 kilohertz. That is your source frequency. The question is really asking you, why is it sometimes above and below the source frequency? Why is it above and below the original frequency of the vehicle? So this one by now you should know is due to Doppler effect. So you can mention something like this. Observed frequency will vary because the vehicle is moving relative to the observer. When vehicle moves towards observer, frequency observed is higher than 1.2 kilohertz. But when moving away from the observer, the frequency observed is lower because that's what you learned from Doppler effect, right? Doppler effect was this. There were only two things that you really needed to know. If it's moving towards observer, observed frequency more than source frequency. Basically, frequency increase. But then when moving away from observer, your observed frequency is less than your source frequency. Your frequency is observed to have dropped. And this is what is being described here. Okay. Then state the name of the phenomenon in B1, which you've just explained. That one is Doppler effect. Okay. Now then on figure 4.1, mark with a letter X the position of the vehicle when it emitted the sound that is detected at time t. Okay, on figure 4.1, mark with a letter X the position of vehicle when it emitted sound that is detected at time t. Okay, time t is this one, right? T is this part here. So just now there is some things here that I mentioned to you in this graph that you have that looks like this. The 1.2 kilohertz is here. Is this blue line here? Maybe I should just draw a line. Okay, this is your FS. Okay, I written here this is your FS. So you are actually going up, down, up, down, up, down, up, down from here. This one is your maximum frequency. Wait. This one here is your maximum frequency. This one here is your minimum frequency. For minimum frequency, this one I think I can draw an arrow here. This one is moving towards observer. This one is moving away from observer. Okay, from the blue line. If I go up, this one is actually you moving towards the observer. If you go down, this is you moving away from the observer, right? So the question wants you to find out what is the position of the vehicle at time t. Okay, this is your time t, right? So at time t, this is your maximum observed frequency. which is the maximum possible, right? So in your case, it should actually be over here. Okay, right? Just draw an X. Just mark out this position and then label this X. And then you should be fine. This is where you are gonna get your maximum frequency. Now it's at this point here that you are actually approaching your observer. Then after that, as you keep moving like this, at this point here, this is where you have the minimum observed frequency. Okay, there's one thing you can actually see from here. I mean, how should I put it? Okay, let's just say I divide it into here. Remember last time I mentioned to you, your direction of motion is always tangent to the curve or whatever path you're following. So in my case, if my object moves in a circle, my V would be like this. My direction, okay, maybe I just write this as my direction. My direction would be like this, always tangent to the circle. So this part here is where you are moving towards observer. But then after that, if you trace the path tangent to, if you trace the tangent to the circle given by this blue arrow here, this is where you are moving away from observer. Okay, so just so you know, it's only this part that you're moving towards observer. This part you're moving away from the observer. But right now we're really just interested in the max value. So max value will be here. Okay, so this is the position X. All right. Okay, then after that they ask you on figure 4.1, mark with letter Y the position of the vehicle when it emitted sound that is detected at 9t/4. Okay, 9t/4. 9t/4 is 2.25t, right? That one will be given by this position here. Wait, no, this one is 2.25t. This one will be 2.5t. Let me just mark it out. This one will be 2.5t. So 2.25t is over here. Okay. So 2.25t is over here. Now at this spot here, this one by right, it should be y here. Okay. You see at this spot here, exactly at y, maybe I shouldn't have drawn this red arrow here. Maybe I should draw a different colored arrow. Okay, now green. At this spot here where it's denoted by y, you are moving here. Okay, so this one you are neither moving towards or away from observer. Okay, you are neither moving towards nor away from the observer, so you don't have any frequency change. You don't expect to see a frequency higher, nor do you expect to see a frequency lower than your source frequency. Okay, so at this point itself, point y, it is not moving towards or away. Okay, so that's why this one is position y. All right. Okay, so that one is okay. Then after that, there's one last part here. Okay, this one we can just do very quickly because it's just talking about the equation. Okay, now they tell you that the speed of sound in the air is 320 milliseconds, 320 meters per second. Use figure 4.2 to determine the speed of the vehicle in B. Okay, Right, so you have two different choices. I think you want to use the equation for moving towards observer or moving away from the observer. Or in my case, I wrote it as approaching observer. So if you are approaching observer, you can just say that Fmax is equals to VW over VW minus Vs times Fs. So sub in the values, you will get Vs as 45.7 meter per second. Or you can also use the case where it's moving away from the observer, where you say F mean is VW over VW plus Vs times Fs. So you sub in the values and you still be getting the same answer. Okay. So your Fmax, F mean, your VW, and Fs, these are all indicated here. All right. So as I mentioned to you, this is your Fmax, this is your F mean. Sorry, this is Fmax, this is F mean, this is Fs. And then after that, your VW is somewhere here, right? I think. Your speed of your wave is given already. All this here, by the way, as I mentioned to you, this is all your observed frequency. Okay. Where you have Fmax, that is moving away, moving towards. Where you have Fmin, that is moving away from. So just sum in the values now, and you should be getting the answer. All right. Here in part C, we've already told you the speed of the sound already. This is your VW, speed of your wave. Okay, so just sum in the values and you should get the answer. You will be getting 45.7 meter per second. All right, so the formula for Doppler effect for approaching observer and moving away from the observer, you should have already committed this to memory already. Okay, the only difference is that either they're minus or plus. Okay, right. So for waves, we are done. Lesson. Okay, last week we were doing November 2021 P21, and then we did up to question 4, right? We were discussing about Doppler effect for that particular variant of the paper. So now let's move on to question 5 and 6 and finish off this paper. Okay, right. So if you look at question 5 of that paper, November 21 P21, state Kirchhoff's first law. So Kirchhoff's first law is just simply sum of current into a junction is equal to sum of current out of the same junction in a circuit, which you all know as this now. Sum of I in is equal to sum of I out. Okay, so this one shouldn't be that big of an issue. Yeah, another thing that sometimes people may have unknowingly made, the mistake that some people may have unknowingly made is that they sometimes forget to write the word sum of current into junction is equals to sum of current out of junction. Instead, what they wrote was current into a junction is equal to current out of the same junction. If you wrote that, that one would not be considered as correct. The key word here is that you must always write sum of current into junction equals to sum of current out of junctions. Okay, if you don't write sum of, you can actually just replace it with total current into a junction is equal to total current out of the same junction. Okay. Okay, now then if you move on to part B, the circuit shown in figure 5.1 contains a battery of EMF E and negligible internal resistance connected to 4 resistors R1, R2, R3, and R4, each of resistance R. The current in R3 is 0.3 amps and the PD across R4 is 2.4 volts. Show that R is equal to 4 ohms. All right, so based on the situation that we have here, they are asking you to show that R is 4 ohms. Okay. Okay, so based on the information that has been given to us, we know that this one, R4 has a PD of 2.4, R3 has a current of 0.3 amps. Okay, that's what we know so far. And then after that, they also mentioned that each of these resistances, R1, R2, R3, R4 are actually having the same resistance of R. So all of these can actually be considered as just R, 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 and then R. Okay, so how do you proceed from there? You can actually single out this portion here. You see, in our case, we know that current I comes out of, let's just say I1, okay? Current I1 comes out of the battery. It flows through R1. That's why it's called current I1. And then the moment it reaches this junction here, it will split up. It will be I2 over here because it flows to R2. And then this one will be I3 because it flows through R3. And then after that, when it combines, but as it continues to flow, it reaches this junction again where it combines back to become, say, I4. Okay. So in my case, what you can see here is this. This part here is a parallel connection. And for the parallel connection, you actually have the same resistance. Okay, so what you can then say from here is that because this is a parallel connection and each of the path has the same resistance, it follows that the current must be splitting up equally. So I will know that this one will be, if this one is 0.3 amps, this one must also be 0.3 amps. Okay, so you can actually just mention on that this now. And the parallel at the parallel combination, maybe I revert this. Each path in the parallel combination has the same resistance. Okay. Each path in the parallel combination has the same resistance. Okay, each path in the parallel combination has the same resistance. Current splits out equally over the parallel combination. Okay, so the keyword is to recognize that your parallel combination has the same resistance. And then because it has the same resistance, current will actually split out equally over the parallel combination. So in my case, since I already realized that this part here was 0.3 amps, this one must also be 0.3 amps. No? Okay, so eventually I can actually come to this relation here. If you look back at this part, just now I said that this one is I4, right? I4 is actually the same as I2 plus I3. In my case, it will just be 0.3 plus 0.3, giving me 0.6 amps. Okay, this is the working right over here. Now, I know the current through my R4 is 0.6 amp. I know the PD across it is 2.4 volts. I can subsequently work out what is R itself. Okay, so if I apply V equals to IR for R4, V4 equals to I4 times R4. So V4 is 2.4, I4 is 0.6. My R4 is R itself, so R will be 4 ohms. Okay, so this is how I find the answer for part 1. And then we can actually then move on to part 2. Part 2 is they ask you to determine the EMF E of the battery. Yeah, so yeah, with this one better just write it as this. I3 is the same as I2 is the same as 0.3 amps. So, okay, this one is just another statement to build up from this. Okay, so if we move on to part 4, sorry, not part 4, part 2, determine the EMF E of the battery. Now to find out the EMF E of the battery, this one you can actually just apply Kirchhoff's second law. This one is pretty straightforward. You just apply Kirchhoff's second law. You can apply across any of the loops now. You can apply across this yellow colored loop, where we will say that E is equals to V1 plus V2 plus V4. Or you can also apply it across this loop here, the green colored loop, where we say that E is equals to V1 plus V3 plus V4. Okay, it doesn't matter which one you use. Just use whichever you like. In my case, I use E is equals to V1 plus V2 plus V4. So I just use IR for each of the resistances. So this one I know is 0.6 and then its resistance of R. R1 was R itself, so it's 4 ohms. So it's 0.6 times 4. Then this one also is 0.3 times 4. This one is also 0.6 times 4. Okay, so this one here I know all is 4 ohms originally just now. Okay, so you just use IR for each of these resistors here to find the PD, and then you sum it up. So eventually you're gonna get 6 volts. All right. Okay, so that one should be pretty straightforward. If you want to simplify this entire circuit, you also can, but I think it's a bit more complicated. I mean, it's not. It's just a bit more tedious. The working that you see here is you actually trying to simplify the whole circuit, where what we are actually doing is this. We say that this one here, this one was 4 ohms. This one here is 4 ohms. This one here is 4 ohms. And then this one, sorry. This one here is also 4 ohms. So you try to simplify it. This one will thus become a circuit that looks like this right now, where we say that this one is 4 ohm, this one is 2 ohms, this one is 4 ohm. Because this is a parallel combination with equal resistance on each branch, we can actually say that the parallel resistance is just 4 divided by 2. This one I think I explained to you before. You just take one of the resistors, you just take the resistance value divided by the number of resistors that you see. So here's 4 divided by 2 giving me just 2 ohm. Okay, so this one you can then further simplify it to become something like this, where we say that in our case, this one will become something like this now. This is E, this one is, because these are connected in series, you can actually just add them out, where you say that it is 4 plus 2 plus 4, giving you 10 ohm. So this is 10 ohm, and then I know the total current will be 0.6, because you see from this part here, you can see that whatever came out of my battery was 0.6 amps before splitting up and joining back. So I also know that the current is 0.6 amp. Okay, so here I can actually say that E is equals to 0.6 times 10, giving me 6 volts. Okay, it also works, just that it's a bit more tedious. Okay, so this one is okay. Then we move on to part 3. Okay, So we move on to part 3. That one is a state and explain question. Okay, so for part 3, the battery in B is now replaced with another battery of the same EMF E, but with an internal resistance that is not negligible. So you now have a battery of the same EMF with internal resistance. State and explain the total change state and explain the change, if any, in the total power produced by the battery. Will there be any change in the power produced by the battery? So here, the obvious answer, common sense would tell you you got internal resistance. Obviously, your power produced by your battery would decrease, but how do you actually explain it? Okay, so what you could probably just say here is this. Just now I actually draw a simplified version of your diagram. I'll just make use of this diagram here that I have okay, just now. Now, if you have internal resistance, just wipe everything off. Okay, so with internal resistance, your circuit would just more or less look like this. With internal resistance, your circuit will now probably look like this. So while you have 10 ohms over here, you now have another resistance here. Okay, so in our case here, your R total is actually 10 plus R. Okay, your R total has actually increased. That's why here I can actually say that my total circuit resistance has actually increased with the addition of the internal resistance. So the current flowing through my battery will actually decrease. If resistance increase, current ought to decrease. Okay, and then since I know the power produced by a battery is actually the EMF multiplied by the current, therefore total power produced decreases. The EMF I already know is constant, is the same here because they already say here same EMF. So if P is equals to EI, E is constant, therefore P is proportional to I. So if I already know that I drops, power ought to drop. Okay, so this is for part C. So this one, I think I better just write it here properly. I total increase, I total drops. Okay, so this one will then tie back to this one. Okay, so this one is all right. Then we move to part D. Part D, we say that the resistors in figure 5.1 are made from nichrome wire of uniform radius 240 microohms. The length of the wire needed to make each resistor is 0.67 meter. Calculate the resistivity of the nichrome. So all you just need to do here is to use R equals to rho L over A. Since you have mention of resistivity here, the only equation in your entire AS syllabus that has mention of resistivity is just this one here. R is rho L over A. Okay, and since they mention radius here, you just change out your radius, you just change your area in terms of radius, which is pi r square here. Okay, so R is equals to rho L over pi r square. Sub in your values now. For the resistor, which was made of the nichrome wire, it had a resistance of 4 ohms. Then it had a length of 0.67 meter. And then it has a radius of 240 micrometer. Just change the micrometer to meter. Remember your square. Then multiply with your pi. Solve and find resistivity as 1.08 times 10 power minus 6 ohm meter. Yeah, there's a typo error here, sorry. This one is not meter, this is ohm meter. Okay. Right. Okay, Okay, Anchi is here. Right. Hi Anchi. We just finished question 5 of last week's question, November 21 P21. So we just finished question 5 lah. Alright. So you're just in time for question 6. Yeah, no worries. The lesson is recorded. You can always review back what we just did. Okay. Alright. So we move on to question 6. Alright. Okay, so let's move on to question 6. This is the last part for particle physics. Okay, so we go to the question right now. Complete table 6.1 to show that the masses in terms of unified atomic mass U and charges in terms of elementary charge E of alpha, beta plus, and beta minus particle. Okay, so this one I think should be quite straightforward since we just recently went through particle physics. So alpha particle, we know the mass is going to be 4U, okay? Because alpha particle is alpha 42, which is the same as helium 42. So I mentioned to you that the mass of alpha particle is actually just 4U. You take the nuclear number multiplied by your unified atomic mass, okay? And then after that, the charge of your alpha particle or helium nucleus is just going to be 2E plus 2E lah. Okay, sorry, plus 2E. Okay, it's positively charged because it's a helium nucleus. Nucleus is always positively charged. Okay, so this one will be plus 2E. Okay, so that one would be okay. Okay, then after that, when it comes to your beta plus particle and beta minus particle, your mass in terms of U is just 0.05 U. Because in the notes, I believe I mentioned to you before that the mass of an electron or your beta minus particle is 1 over 2000 U. So you take 1 over 2000, you're going to get 0.005 U. Okay, so beta plus particle is antiparticle of beta minus particle. Okay, so this one, what you just know is that they will have same mass, but opposite charge. Okay, so in my case, both beta plus and beta minus would have the same mass, 0.005 U, but in terms of the charge, beta minus particle would be negative U, beta plus will be positive U. Sorry, not U. Beta minus particle will be negative E, beta plus will be positive E. Okay, so that one is for this one. Okay, then you move on to part B. B will be telling you that carbon-14 is radioactive and decays by emission of beta minus particles. Nuclei do not contain beta minus particle. Explain the origin of the beta minus particle that is emitted from the nucleus during the beta minus decay. Okay, so you're talking about emission of beta minus particle. This beta minus particle was not originally contained inside the nucleus. Okay, so they're asking you, how did this beta minus particle suddenly came about? It wasn't contained inside the nucleus in the first place. So it actually came from your beta minus decay as a result of one of your nucleons changing to another nucleon. Okay, so we know that beta minus decay is where a neutron changed to a proton, and in the process you're going to get a beta minus particle and an electron anti-neutrino. This is kind of like the byproduct of the result of neutron changing to proton. Okay, so how did the beta minus particle came about? Is because your neutron decays into a proton, an electron, and a a neutron decays into a proton and then an electron. A neutron decays into a proton and an electron. You don't need to write the electron anti-neutrino, but if you wrote the electron anti-neutrino as part of your answer, is also fine. Okay, the two main things they want to see is just the mention of your neutron decay into proton and electron. Okay, for part 2, state the change in the quark composition or carbon-14 nucleus when it emits a beta minus particle. What's the change in the quark composition? During the emission of beta minus particle, we know that a neutron changed to a proton. The quark composition actually changed from up down down to up up down. So here you can just say that a down quark changed to an up quark. Okay, a down quark changes to an up quark. Or you can just make shorten your answer saying that down changes to up, down to up. Okay. And for the last part, suggest why beta minus particles are always emitted with a range of different energies. Okay. Now this question almost always, I mean, it does come out quite often. They will ask you why is it that electrons are always emitted with a range of energies or range of kinetic energies. So the standard answers are always this. Your beta minus particles are always emitted with their electron anti-neutrinos. Okay, electron anti-neutrinos are always emitted with the beta minus particles. Whatever energy is released during the decay is actually shared between the anti-neutrino and beta minus particle randomly. Okay, but you don't need to write the word randomly. You just need to know that whatever energy was released usually is split between the anti-neutrino and beta minus particle. They don't share the energy in equal proportions. They don't share it by a fixed proportion. It is random. Sometimes beta minus particle may get more, sometimes beta minus particle might get less. Okay, but the answer is always this. Okay, you have to mention that electrons are always emitted with the neutrinos, anti-neutrinos, sorry, and then energy is always shared between those two. Okay, so this one is nuclear physics. There's also another answer for this one, but this one they talk about the first point was the same as the one that I just wrote. Electron and antineutrinos are emitted during the decay. Momentum is shared between the antineutrino and beta minus particle. So this one is not talking so much about the energy, it's talking about momentum, which kind of relates to energy. Okay, because you are having a momentum shared by different amounts each time, your momentum is P equals to mv, right? So if your momentum is different each time, your velocity is different each time, so your KE is also different each time. Okay, that could explain why your energies are always different, because your momentums are always different. So your speed are always different, your KE is also always different. So you have range of energies. Okay, so this one is okay.